What I do remember it is -4, the fourth to last lecture on quantum field theory, and have been calculating within interacting. Well, our goal is interacting quantum fields. But we've been looking at correlation functions, and we practiced solving them in the free theory. So, what was the? Well, let's go for the new one. We had. We've done. So this LSC says you need to find in order. It's a formula that gives us the scattering amplitudes a set of incoming particles, a set of outgoing particles, and you want to know what's the probability that with your in preparation you get this certain out space. And the formula gives you this in wants you to input. So here it wants you to input time or there's no space for it. It's very long. Time ordered correlation functions of all your fields, and you need as many as you have here in total. Let's see. So this is what we need to compute. This is what this formula tells us, and then we have to Fourier transform it, and then we have to find the coefficients of certain poles, and then read out those coefficients, and this is essentially the amplitude. Now we're here, we want to compute this thing, and we started practicing computing these things in the free theory. So then the vacuum was called the 0, and field phi is just the free field evolving with the normal free Hamiltonian, and the creation and relation operators were time independent. Everything was kind of simple. So except for then this time ordering. So we practiced that, and the time ordered 2-point function of a field in the free theory we called the Hyman propagator. Without the F, it's without the T, and then you have the propagation always from the right event to the left event. The time ordering is the propagation sometimes from there to there or from there to there, depending which is earlier. You start from the early to the later. That makes kind of physical sense, but it's quantum field theory. You don't base it on what makes physical sense. For a very long time, particles went back in time. The reason why we care about this one is because it's here, and that appeared in the derivation. There was a mess of oscillators, and we wanted to push them somewhere, and we weren't really allowed unless we remember how they were ordered. So this is the memory of that. We reordered them, but this puts it back where they really belonged in time order. Time order, just because here this is in and this is out, and that is made its way through here. And this is a very cute representation as a momentum integral. And then there's a p squared minus m squared I e to the minus ip x1 minus x2. Except for this didn't have a well-defined value like this. It has a pole, 2 poles in the P0 integration, and we moved around those poles to give this a value. And if you move in a certain way, which you can remember with an I epsilon there, it shifts the poles off the real axis, and then when you go along the real axis with your P0 integration, you just go around those poles in the right way to produce this time order. So that's what we have. And in the homework you have, or you are still working on it, the time ordered correlation function of two fermions and two photons, and they look very similar. So let's assume we know how to compute time ordered 2-point functions. And then today it's the higher correlation functions. Three, four, five, 6-point functions. And there is a rule for that too, and that rule is called Wick's theorem. Right. And once we have that, this is the formula that gives us, it essentially reduces the endpoint correlation functions to a sum of products of 2-point correlation functions. And once we have that, then we have to go back from here to here, and that will also start today. We have actually a lot to do this week. It is, well, there's some very lengthy and kind of boring derivations, which you wouldn't ever be able to cover in just 2 lectures. It's just too much writing. So it's all written down on 21 pages for you in all details, but here in the lectures I'll highlight the things. So you should understand the idea and where things are coming from and what's the meaning of all these equations, rather than following every I and minus sign from one line to the next. So that's kind of the idea. Just shout if there's something conceptually, or anything, just shout at me if you have questions. Now, the idea is to look at, we are looking at 0 and then time ordering, and then we have, so this is the free theory, right? Free theory. Time ordering, and then they're just called phi. And then they stick a bunch of space-time points. And I will usually label them 1, 2, 3. Here I'm going to label them A, B, C, and so on, because I don't know what their times are. I have a certain number of them, and I find now labels for these coordinate. This is your space-time. These are just some points. This is called A. This is called C. This is called B. These are the points in your space-time. Right? These are 4 vectors with the time component. O is the time, and this is the vector part. And then I will now call this point, which was XA, I'll call it X1. And this XC I'll call X2, because it comes in the time ordering second place. XB I'll call X2. So I am introducing new X3, thank you. That trace helps me. So let X1, X2, X3 be a permutation, the permutation of XA, XB, XC with the requirement that the time of 1 here is the first, X2, X3, and so on. So now I can get rid of the time ordering if I place, I don't know which one that name is, if I place them in such a way that the labels are descending. Okay, so now I've taken care of this time ordering, and at the end, I'll see what happened. What happened? Like if we have a formula for this, if I want to go back to ABC, so that we have a general formula. I like your formula. It goes here, da da da. But at the moment, I make this assumption that's relabeling and then I have it. So we're looking at that now. In the free theory, the actually always, but here's useful. The fields have this expansion, D3P, 2 pi, Q 1 over 2P, and then the annihilation operators, P, e to the minus IPx. And then another term, which I usually write under the same integral, but today is different. There it gets its own integral, I p times x. Okay, so this is the usual mode expansion. I want to call this thing phi of x1. Why is there no 1? If it has to put no. Let's see, we do this for all xi, xi, xi. That's the word. So this is xi. C for creations. And this is I, xi, annihilation. And B is for creation. Then I can write some more complex formula. So now the idea is to start from the right and see what happens. Apply the field to the vacuum. You know how this works, like the annihilation operator killed the vacuum. And so we only have that, and then we'll act with the second, and then with the third, and then we see a pattern sooner or later. Let's say we have just one field. So I'm looking at phi. Also, let's introduce the following shorthand. Phi I is just phi of xi. So instead of, you know what? Shall we skip the heads for it? No, I promised myself never. So the index on the field is the index of the argument. It really gets lengthy after a while. So what we were doing is now phi 1. So the field at x1 at the earliest time acts on this. So now we have annihilation and creation. And this is 0. And this is, we don't know. We have to keep it. So that's our first formula. Two fields. It becomes it will make more sense. This is just a bit empty. If you have only one field, you would be done. Like the 1-point function, you came with the vacuum from the left, and nothing will be left over. Then it would kill this from the left, and then you have 0. So yeah, this is a boring first result, but it is 1. So let's go to 2. And now we have phi 2, phi 1, 0. Here I insert what I had before. And this one I split into a annihilation and creation part. And this one's just the creation part. Oh, now, what do we get? I have to multiply this out. Phi annihilation, phi creation, plus phi 2 creation, phi 1 creation 0. What are you proposing? Simplify, and really the only way that we know that things simplify is when the annihilation operator hits the vacuum. There, the commutator. So if you push this through, then the A hits it. So let's postpone thinking. Let's just do the commutator. Phi A and C, 2, 1, whatever that is. And then the other term that we've added, the one with the other order, came with a minus sign, so I added back in phi 1 C, phi 2 A. So all of this is the first. The first term of the commutator is what we have. The second term of the commutator cancels this. So it's what it is. And then we copy phi 2 C, phi 1 C. Now, why did you do this? This is 0. So that's gone. And now we start to think about what's the commutator doing. How much is that? So in fact, we've done something like we've computed the commutator. Well, what we've computed is the commutator of two fields. Now it's only part of it. So now we have to commute this thing with this thing. That's easy enough, right? You'd be able to commute A with the A dagger. You have to have a different integration index. So this is P and this is Q, say. And then you use the commutator of A with A dagger. This is identity, and so you found. Another way of getting it is realizing that it's not an operator anymore, which we see from what we just said. If you commute them, you have an identity it's an identity operator if you want. It's a number times an identity. It's a function times an identity operator. So if that is an identity operator, then we might as well phi A C what 2 1 C multiply this by basically that. That's the same. We might as well stick it inside. Phi A 2 phi 1 C 0. That's okay because this is just a number. So taking the expectation value doesn't make a difference. But once we have that, we can see what we see. You know that this can be completed. I'm going to see this quickest. This is phi 2 A phi 1 C minus nothing, right? The other one is nothing because it has the annihilation operator here. So it's this. But this I can complete with both fields. Because I have to add to this one the creation part, which is 0. I have to add to this the annihilation part, which is 0. So just this little, the fourth basically of this is the same. Do the other way around. Right here, the sum annihilation creation for both, and then the 3 terms disappear. And this is by definition the d without the f of x2 minus x1, which I'll call now d21 because arguments are now indices. There's no magic. You could have written these things, the commutator between the two things, you would have write down integrals. And I didn't want to write the integrals, so I went this way. Either way, the commutator of two fields is this propagator, not time ordered. Does that make any sense? Like even if you don't look at the details. When we discussed the microcausality, we had the commutator of the field at different times, and we saw, oh, this is related to this commutator in one particular form. Now let's use it here. So we find phi2, phi1, 0 is here comes the commutator, and I write it to the right of the 0 so that I know it's gone. So the identity operator part sits here, and the function sits there. Plus phi c 2 1 0. So that's formula number 2. That's one. And what I want you to remember is this commutator thing. The commutator of whatever I with J, annihilation here. What I really want is I spell the commutator out. If an annihilation operator at position I is to the left of a creation operator on the right, position then you can turn them around. See, I just turn them around and add a propagator between I and J. This is what we've done here. That's the first term of the commutator is this time. In the negative, I've pushed to the other side, and that. And the order here, 2, 1, is the order 2, 1. So the first term of the commutator, Ij, is this Ij. That makes any sense. So this is actually useful when we go further. We'll apply this again and again. Now, three fields. Phi 2, phi 1 on 0. I'm using the decomposition for the QFT, and the result for 1, 2 from there. So that is 0, d2, 1 plus phi c, 1. Now, which one first? I don't know. Let's do the C first. Then we get phi c at 3 on the vacuum, d2, 1. Then here we get all three, phi, c, 3, 2, 1 on the vacuum. Now the annihilation shows this. Oh, finally something. And then on here, plus phi A, phi C, 3, 2, 1 on the vacuum. What do you do next? Yes, yeah, you want to do that? Okay, so we are going to move this A to hit here. And now we have to go 2 steps because there's a C next to one. We can use this formula and use it twice. So this thing is, let's really space. I switch them around, and that costs a propagator. So plus phi 1, 3, d 3, 2. This I can push anywhere. Before or after, I don't really know where I want it. D2, that was the original order, phi C1. I guess I want it like that. And now one more. So this is phi 2, phi 1, phi 3 with the A. But that cost phi 2 here at D1. And this I can copy D32 phi 1C. Now, here and here. And we can order them a little bit. Let's say this one first. It's phi 1, D, X on this vacuum, and we have a D2 left. Then I'll pick this one, plus phi C2 on the vacuum with a D31 left. Then I want this one because it is a single creation operator. And it comes with a D32. Now I have what? I had already. Fine. I take this one. Phi 3, 2, 1. So let's see. I have this one written down. This one I haven't. This is 5 by 5, C, 3, 3, 1. Now I have it. And this is 3 terms. This one gets killed because of A to the right, and these two I go here and there. Okay, good. That's what we get for 3 fields. Getting better and better, 4 fields. The question is whether we go, I think we're going to skip that. We will think hard what we get. So we have pi 4, 3, 2, 1. So that means on this result, we have to act with phi annihilation 4 plus phi creation 4. If you do creation, we get 2 fields in front, 2 fields in front, 2 fields in front, and all 4. If you act with annihilation, it takes one away, takes one away, and here it's going to take also one away, so we are left with 2. Nothing will be left here, except for the vacuum, and here we'll have 3 times 1. So let's organize the terms that we are getting according to how many creation operators act on the vacuum. The least will be if they're all gone. So I can only get this if I ever have the phi A acting here, right? So if the phi for A acts here, it kills this and gives it the property there. So then we have the 0 times D for 1, D 3, 2. Does that make sense? I'm acting with the annihilation part of the 4th field here. Imagine here an annihilation operator comes here. I want to push it through. Pushing it through costs a propagator, and that's this propagator of the 4 with the 1. And yeah, and then the rest survives because the pushing it through, produces this term. The one where it is pushed through is gone because then the A hits the 0. So that is applying A4 on that. I can act here, and then I get the similar thing, 0, D4, 2, because 4 and 2 needs to be 1. And one more plus 0, D4, 3, and then there was a D2, 3. So the pattern really works. We have 1, 2, 3, 4 indices, and they're all there in the various combinations. That's all the terms that we're ever going to get with just the vacuum. Now, the single one we won't have either. Now come the two. We can get it from the C acting here, here, or there, or the A acting in the back. Let's do the C on the first page. And then I just need to add it in, right? So I have phi 4 C phi 1 plus phi 4 C phi 2. See? There should be missing. E 2 plus phi 4 C phi 2 C D 4 E 3 1 plus phi 4 coming 3 D 2 1. Ooh, okay, so the creation part on these two. The creation part on this one I'll leave for a second, or I don't want to forget it. 4 3 1 2 1. Okay, so now we're done with the C everywhere. But here in the middle, I want to have the other terms with the two creation already, and they when the relation part of this is this. And now, okay, so assume it's here, and we push it through once. If you push it through once, you get a propagator. So it's phi 2 1 0 D 4 because we push the 3. Now you imagine it's sitting in between because you push it through. In this other term, it's here. So I now push it through the 2. Then I get a propagator of 4 and 2. So D 4 and 2, and left are the 3 and the 1. Now it's sitting there, and I can go one more time, and then there's the 3 and the 2, and it's 4 and 1. Now I have everything. Because when it is on the other side, it just has to produce a 0. And this looks very messy. And let's see if it makes sense. Like it would be weird if a certain combination isn't there, and if one is twice, and let's see what we have in this mess. And people came up with a graphical notation for these terms. Since we have this order here coming in, we'll always write 4 3 2 1. This one could somehow connect index 4 and 1 and 3 and 2 with a propagator. So it looks like there's a connection, and that's what they write. This is now a way to denote that first thing. So this is supposed to mean D 4 1 B 3 2. Now what is the second one? That's not so hard to guess. Plus you want to guess it anyway?
Yeah. So the same with 2 and 3 and 1?
Exactly. So now I think, at least for the visual people among us, this looks better than all these numbers. I mean, what are the numbers? When you see the numbers, you have to kind of put this in a geometry, in a picture. So then we have 4 with 3 and 2 with 1. And now we can stare at it and see, is there some kind of connecting them forgotten or what? But no, it looks like if I gave you four ordered points and I asked you to connect them up in pairs, like here, you 4, find groups, how many groups of 2? How many, like, what groups can you find? Where can you find? The first person needs to have one partner. Okay, so there's three options. This one, or this one, or this one. So there's three different things, and one that is picked, the other two are bound together. So, it's just these things. These are the three. These are all the ways how you can join up the four fields. What is the rest? They are not fully grouped. So the first one is 4, 3, 2, 1, and only 2 and 3 are put together. And 1 and 4 are still on the search. And then we have 4, 2, plus 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. How many are there? 1, 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1, and 4, 3, 2, 1. Now, this is 1 and 3, this is 4 and this is 1 and 2. This is 4 and 3, this is 4 and 2, this is 4 and 1. Now, what is this? This is all the different ways to connect just two, and leave the other ones unpaired. And there are 6, and we have all 6. I guess we have all of them. And that is not connecting anything. And then you have, so now, knowing this, I think it should not be hard or very lengthy to tell me what is the answer for 16 fields. No, n fields, I guess. So 5. I don't even want to. I don't even want to like this. But you know, right? It'll be everything fully paired. What if I have 5? How do we know 5? Let's look at 3. What do we do with the third one? The third one will look like this, right? 3, 2, 1, and then the first term here will just connect them. So 1 will be always open, and then 3, 2, 1. Where am I? My answer then?
It's just at the top.
Should be able to figure it out, right? So there, the first term was 3, 2. And then 1, 3, 1, 2, 1, and then 3, 2, 1 without anything. So if it's an odd number, you just can't have everything connected. By the way, I have to say this now. These things, these lines are called contraction. A contraction. They are contracted. I don't know why. Maybe they have a contract, but somehow they are contracted. And yeah, so it means the sum of the maximum number of contractions, all possible contractions, plus 1 less contraction, plus all possible ways of contracting with 1 less, and then and so on until you haven't contracted anything. That's this answer. I don't want to write it down. I'm going to write it down when we have come with the vacuum from the left, because this is still what we want. We want the expectation value, so there has to be a phi 0 from the left. And if the phi 0 comes from the left, what does that do? All these C's that are around here will annihilate that vacuum that comes from the left. So there isn't not much left. What is left? If now I came here from the left with the 0. Yes.
And in the picture on the right, for only the top line.
Because
it's the only one with no creation.
Exactly. It is here. This is the one with the naked vacuum, And the vacuum from the left and the naked vacuums are good, and the vacuum on this is just not good. So it don't get killed. So it's much simpler. And if you have three fields, you know that any odd number of fields wouldn't give you anything, because if you have an odd number, there will be at least one lonely, and then with the vacuum it is zero. So we only have even number correlation function here.
I have one question. Since the D is not symmetric in these, but
No.
the contraction somewhat.
No, it somewhat isn't. It isn't.
Is it just because we?
It isn't. Dot, I, dot, J, dot, is equal to D, I, J, not J, I. Don't turn them around.
If I read it off, I can't like. Okay, so it's always from the top, from the higher number to the lower number.
No, it's always from the left to the right. This indicates, however, that coincides.
Okay, so if we write 1, 2, 3, 4, then we have the.
Yeah. But you were onto something. This is exactly the discussion how to put the time ordering back. But let's write first the formula with the thing on the left. So it is time ordering. Gosh, time ordering. You didn't want time ordering. Phi x n phi x2 phi x1 0 is equal to all possible full contracted, I guess. Fully contracted, full contracted. In words. And, that was an example. So the example is phi four, phi 3, phi 2, phi 1 is equal to, I can draw the picture. Let's do the picture again. 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. So you start, you sit down, and think how many times, how many ways can you do the full contraction? And then you see, oh, these are the 6 that we had. And then you just copy it and write the D. And for every contraction, every bracket, you write D, and you stick to the order. 4, 2, 3, 1, 4, 1, 3, 2. You can change the order of the propagator. This, you can switch to the other side, because you wouldn't even know which one has to read off first. Here, the one because it starts early, or the one that finishes there. I don't know. It's your choice. You can change the order of the D's, but you cannot change the order of the endpoints. And now this is your answer. Now this is the formula again. This is not words or finding pictures. This really is equal to the product of these objects that we have defined as net. And now comes what happens to the time. If you want to go back to A, B, C, D, where we don't know what the order is. From the labeling. We have a time ordering operator in there, which will order them, but from the notation, we don't know. So I want the formula for T of phi A, phi B, and so on, not A, B. The index is here. It went back. Shortening time is over. I want this. So I have a time ordering. And then we said, okay, I have a permutation of names for the space-time points. And then I move from here to here, and then I have 1, 2, 3, 4, and I know that they are ordered, and then I don't have to have my T. Then I get this. And now I would like to figure out which of them is the A, and what would I do? So, the answer that we get here is always symmetric in all pairs. And symmetric in all pairs means that there's no pair that is treated differently from any other pair. So the pair like 1, 2 appears here. You know, I don't understand. I don't even know how to say this. Since we have all the pairs, each pair, you know, you think you're 4, and you want to know, am I treated fairly? Yeah, you have one, the partner, whoever it is, but there's nothing that singles you out. You always paired with girls, right? No, you're not. You're with everybody equally. So the pairing.
4 is always first.
But within a pair, exactly, within a pair, it's not. You, the oldest 4, are always the head of the team. So the teams are kind of fair. You pair with everyone, but within a team, there's a ranking. So it's not completely, every field is the same, but there's just the boss, right? There's the oldest, next to the left, and he'll stay the boss within the pair. Oh, but that is good, because since we've, these are labeled such that this is really older. This is the later one, as all of them. They are here within the indices on the D, they are time ordered. So every D has time ordered indices. And so if these were now the ABCDs rather than the 1, 2, 3, 4s, but we need to see it, we'll just say, well, they need to go to the left. What does that mean? It just means we have used the assignment properly. So if you have a one without the time ordering, you just put the D's. If you have a time ordering, you just put the DFs. So this is the same formula, all possible full contractions using the assignment properly. DF. So this is now almost too simple to write down, but let's do it anyway. Phi A, phi B, phi C, phi D is equal to DF, I guess AB, that's in brackets, the parentheses, XA minus XB. Why not? D F XC minus XD, DF XA minus XC, DF XB minus XD, and D. Oh, what does that mean? All sum of. Here's the plus DF XA with XD and XB with XC. So it's the same formula like there, just if you have the time ordering in your big correlation function, you have to have the time ordering in all the 2-point functions. And then all of this is now called Wick's theorem. But to be honest, Wick's theorem, it gives you also a formula without the vacuum expectation value just for the time ordering, but then you have more terms, the ones that we put throughout, you have them, but we don't need them. We don't care. This is baby Wick conversion, basically. Baby Wick. Well, that was fun. Well, okay, if you have different fields, what if you have different fields? I've used the scalar field notation, but the whole thing is just based on the commutators. We are talking about the free theory, and they all have the same mode expansion. So even if there's an A, we just write it as an AU annihilation plus an AU creation, and the whole thing goes through in the end. So let's say this was a vector field A mu, A rho, and A sigma. They carry a vector index. And then you do the whole thing and you carry the vector index around, and then you have a 2-point function of all the pairs. These are the 2-point functions. So if then you have this with this, it has an index mu. Okay, if I do a final propagator for a vector field, it has 2 indices, mu and u, as you have for, we'll figure out by Friday. And if it's a spinor, then it has spinor indices, and then you have your final propagator with spinor indices, but it's just the same formula. Except spinors, there's what Grassmann thingies, right? So careful when you commute them, right? They anti-commute. So what it if you have some size, right? Psi, and then they have to have bars. Psi, bar, whatever. Like, yeah, that looks fun. And then we have 1, 2, 3, 4, 5, 6. And then somebody has a contraction for you. This. You'd want to write this as psi 1, psi 3, psi 4, psi 6, and the propagator basically of 2 and 5. I'm suppressing all the spinor indices because I'm talking about Grassmann. So then these have kind of moved together and then join this. So I have to jump. The jumping is taking care of the contractions, but the sign, we haven't done the sign. So if this moves, it wants to go next to him, immediately to the next, to the left of him. So it has to jump once, twice. Well, that's boring. So sad. So it jumps twice, right? So I'm going to get 2 sides. Nobody would have noticed if they had forgotten. But that's what it is. So we get a sign twice. Then they're next to each other, but if they're next to each other, that's not what I have. I have the 6, they have moved out. But once they are paired, they are good. A pair of Grassmann numbers is like behaves like an ordinary number. Because if you pair, so if you find another Grassmann number, you're in a pair now. You find another Grassmann, you want to go through. Then the first one gets a minus sign, the second comes after, it's another minus sign. So if you move as a Grassmann pair, you move freely, basically, without extra signs, without warring. So once they are close, you can push them where you want. For example, out. All right, so this is the sign. We wouldn't have noticed if I had made a mistake here because it's squared, but there are these signs. There's no contraction between psi and psi, or psi bar. Just because the psi has the A and the B dagger, and we cannot contract the two of them. They just commute, or rather anti-commute. There's nothing touch, but if you have a psi bar, this has a B and an A dagger. And these don't anti-commute because then they increase and they increase. So that's also nice. In all these fermionic contractions, you don't need to worry about these two together, for example, or these two together. you can write down all contractions, but if there's no propagator for them, then it will disappear. So I could, let's do one more fun example, where I have time ordering all, and now let's go wild. Phi, A, psi, not a phi, not a A, what? Let's go really wild. Psi bar, phi, yeah, maybe not so wild. Blah blah, we're going psi bar. Cool. So this is lots of fields like 1, 2, 3, 4, 5, 6, 7, 8. If I want to put 8 into pairs, there is 7 double factorial. This is like hundreds. It's 7 because the first one has to pick from 7, and I have a pair. And I have only 6 left. 6, the 6 has to pick from 5. So this is 7 times 5 times 3 times, and the last one is picked the leftover. So there's very many terms in principle, but of course I can contract pi with A. The oscillators don't do anything, so there's no Feynman propagator between them, so that doesn't even exist. And then there isn't much left. So the A needs to go with the A, the phi needs to go with the phi. And then really I have only these 4 left. And now I know that the psi doesn't talk to psi, only to the bar. So there's 2 up. This is just 2 terms. The first one is these 2 together, and then these 2, or the second would be these and then these. So I mean, even if you have many fields, if they're all different and don't talk to each other, it isn't so bad. So nobody will ask you to compute a 16-point function of the same scalar field, probably. But this is an interaction, and then, yes. So that was that story. I don't understand how we ever gonna. Do you have questions about the free theory? 2.3, 4.5. This is fairly fun stuff, basically. It's just all the contractions. And now we do have to shift back to the interacting theory. And I really don't see how I'm going to. Of interaction picture. It should be called also magic formula. At the end, there is the magic formula. And I think I'm going to give as a under my trick, my magic formula first. So what we want is omega t phi Heisenberg x1 phi Heisenberg x2 up. This is all interacting, meaning they satisfy equation of motion with a complicated Hamiltonian. Let's say the Hamiltonian of our theory is the free part, For the scalar field, that would be phi squared, with gradient squared, plus m squared, phi squared, just the simple stuff, the quadratic one. In the oscillator base is just the number operators. And then we add whatever the theory gives us to it. So that could be a cubic term, a quartic term, something nonlinear to it, to this thing. So that'd be simple. And the time evolution of this field here, which I call H for Heisenberg picture, not Hamiltonian or whatever, is like this. The time derivative of this thing is the commutator with the full Hamiltonian with this. So that's what it just is. And it has a formal solution, as you know, that the phi h at some time t. I'm splitting now x and t again up to see the time evolution. It's e to the I h t minus t0 phi at some initial time e to the I h t minus t0. Now I have to figure out where to put the minus sign, but either here or there. And every term is gone. So if you take the derivative, then we should match this. So we want minus I, phi, and h in the back. H in the back is here. So if I do the derivative of this t, then it comes on I. So I guess I want the minus sign there. Huh? And when it is in the front, that is the front, it's the negative side plus the side of this. So that is how the field evolves. I'm getting so excited that my glasses are fogging up. Yeah. Now, this is still what we want. And this state is the vacuum of the full theory. And zero energy, so H on omega is zero. That's what we know. We know it has no momentum or angular momentum, all the things that we have. This is what we want. And we could also do a mode expansion for this field, but the creation relation operators will be time dependent, and then we wouldn't know how to do what we just did, the commutation. We wouldn't know how to commute them at different times. So the trick now is going to be to change to other fields, call them auxiliary fields, fields that we just need for the computation, which by construction we will say evolve with a free Hamiltonian. So we just define, and we call it I, or interaction picture, and we want this at time t to be e to the, they copy this formula here, but I'm writing the zero. So phi I e0 h e to the minus I h t minus t0. Okay, so this is what we define. We define the I, that it has this evolution. That is not an equation of motion that is given to us by the general canonical procedure. This is the one that's given to us, and we introduce a new field, and we want this. And why do we want this? If we have a field with this time evolution, then we can do the mode expansion, and the oscillators in this mode expansion will be constant, and we can set up a formalism as in the free theory for this. Funny thing is completely unreal. It's at this point, it's just a wish for a time evolution. And also we can't just replace the phi h with the phi I in there because so what one has to do basically when so this product of operators will act on states, and they act at different times. So there's something happening from one time to the next. And what is happening is all encoded in the time evolution of the Heisenberg field. If we now take away that time evolution and just evolve it with the free Hamilton from here to there, then we're not getting the full thing. So what we have to do is you have to think of between, you have a state, right? These operators act on states. So there's some state where the field acts on, and then it produces another state. And then we act with another one. So when we've acted with one of the simpler fields at a certain time, so let's just say I would do that. Phi I x2 and then phi I x1. I replaced naively. I'm doing a mistake, right? Because when this acts, it has its form, and then this is it's a little later, looks different, has time evolved here, but only with the free part. So I have to put another operator in between that does basically the rest of the evolution. I have the state here, and then the state needs to the state needs to help us out. The rest of the evolution needs to be, so here it needs to go U for unitary, like for evolution. There's a time evolution, and then you can do all of this. So the formula that you will have in the end will be these fields that we designed to behave as free fields, and the price we pay is extra stuff in between, which, like, from the meaning of it will be to do the other time evolution. This is basically from here within the field phi I, it's the evolution with the free part, and this will be the evolution with the interacting part. And now there's a time ordering all around it. And so I can push these things around, and all the U's that come here, I'll be able to join. So there will in the end just be one single U, which does the time evolution, from the very first to the very end. And it even involves this vacuum to, where's the other vacuum? This one has a vacuum too, which is the interaction annihilation operator. The annihilation operator is in this mode is going to be essentially annihilation. So we have basically a free vacuum too. In this auxiliary free theory, we have a vacuum. So even that we can relate. And the formula in the end, I wanted to give you the formula first. Is this. It is equal to that simple mathematically very simple vacuum, and then the same time ordering of the I fields x1, x2, and then a funny big U. Let's call this U. Let's call this U infinity. That's all of it, and then time order results, and then boom, and that's almost good. You have to divide by U infinity just for normalization fun. So your endpoint correlation function in the interacting fields or the exact vacuum can be rewritten as an endpoint, just as many as points, endpoint function in an auxiliary free theory divided by some normalization, and this U infinity thing is null space is well, to go here, U is defined as the time order exponential operator minus I integral d4x of your Hamiltonian density, the one that corresponds to here, we might as well what's more confusing? New notation is more confusing, so we'll stick with the time thing here, and then have the straight H. The straight H is just the spatial integral of the curly H, which is the density, Hamiltonian density, and this is Hamiltonian. So because I've introduced this, I stick to this notation, and boom. And then here I'm going to mark as an indicator. This is written in terms of the interaction fields. So you're taking whatever you have as an interaction Hamiltonian there, it was given to us by the procedure, or I don't know, what the theory was given to us, and it is written in terms of the full Heisenberg fields. Just take them out, put an index I in there, just take your friendly fields, the free fields, the ones that evolve like this, and use the same formula for the interaction, just write in terms of the phi I, the ones that you can handle. And then, that's what that means, you have an integral and from minus to plus infinity, which is this infinity, so it's just the whole thing basically. And it needs to be time ordered, so in this exponential you have different powers, and this is time dependent. So you have to order it, and this goes in there. That's the formula. You don't know now where it's all coming from. I didn't tell you where it's coming from. I kind of motivated where these things were from, like the U coming from, because of we wanted to evolve them simpler in time, and then we had to make up for it. The point is for the rest of today and tomorrow to derive this formula. But this is the answer, so that we know where we're going, and it's going to be messy. But the answer is kind of pretty, and we have to clear up things by along the way. You know, this infinity limit has to be taken in a subtle way. And yeah, 37. No, I can't waste any time because there's pressure. No, don't get your computer out. We started late because of the technical issues. We do some fun thing. The annoying derivation, I think, let's be super funny and skip to the end and apply the formula. Let's just apply that formula. Let's do an example which fits exactly in our time. I'm so excited. This is going to be good news. And it's the implication of the Wick theorem, because what does it do here now? This exact formula is mapped to here, and now we have these free fields that behave like free fields in their vacuums. And this, all right, so this is an exponential of these fields. This is just going to be many endpoint functions. This is going to be a sum in the exponential. It's a sum of powers of these fields, and it's just so this is the price we pay, right? We have only n fields here, we have n fields down, but the U is going to be a series of very many fields. And let's just look at an example how this is applied. I think it makes even more sense to start with an example. Let's say we have our Lagrangian of a Humboldt field, and adding or subtracting this famous pi to the fourth. That's our extra term. This is Humboldt and this is extra. What's the Hamiltonian going to look like? The Hamiltonian is the normal one. So that's what we have. And now this one comes just like this term, you have to have Lagrange transform the mindset for lambda or factorial. So 24 basically phi to the 4. And this is if you want, you can write Heisenberg here. That's what it is. And now, so here, this is H0, and this is H8, and it's written with the hypersphere. Now we're supposed to replace it by the I. So our H in, let's label it I, H and I is lambda to the 4 factorial phi I. And it's this, okay, sorry, it's the straight H. This shouldn't be the straight H if you don't have an integral. Right? Since I wrote straight H, I'm going to add the integral. And this is based, I don't know, it's the curly then. So here I need an integral over this. So that's what it is. This is our interaction Hamiltonian written in terms of the interaction picture fields. And that is just the coupling constant. This is a funny number. And so what is this U? The U is the time ordered. In fact, I don't think I need it. No. It is the exponential of minus I lambda 4 factorial integral E4 x phi I of x to the 4, right? The time integration with the spatial integration is a 4-dimensional integration, and then I have all the factors in. And so now we start expanding this. This is equal to the unit operator minus I lambda of factorial integral E4 x I x to 4. Some order we're not going to forget. And then the second power. Second power is plus 1 over 2 factorial from the Taylor expansion. Then we have minus I lambda 4 factorial squared factor. And then we have integral d4x. How does that work? Squared. What's that? What do you square an integral?
I don't know what the question was. No,
right. So we have I think that's what you mean, right? And then it's all squared. So this is basically 2 integrals. Right. And so the time ordering is only catch here. Because if I have integral over the time component, he is going to watch it. If he's going to go, he's going to push it to the front. So there's some going on. No problem for us because we have time propagators and all this pushing around is done by the little F index. So that's how it looks like. And say, for starters, because I guess now, you can look at the denominator. Why shouldn't we look at the denominator first? Instead of pushing it. So let's see what this is. So we insert the first one. The first one is easy. This is just 1. And then we have minus I lambda 4 factorial integral d4x 0 time ordering 5i 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 0. Right? I just spelled it out. The 4 powers to see them next to each other. This is what we have. So beautiful. And then down here. Well, there. We need this. We don't. plus, actually, this is minus lambda squared over, oh dear. Oh, that's a lot. That's 2 times 24 times 24. I'm not gonna do that. And then integral d4x, integral d4y, and then time ordering 5x y 0. Okay. These are 8 fields in there. Let's do it. We'll then you can go. Then you can go. So what is the first one? Tell me the first one. You have to contract all 4 contractions. There's nothing in there. 1. Now minus I lambda 24 integral d4x. Now we've just done it. Huh? All the contractions, right? Yeah.
Yeah, all at the same time.
That's fine. So what do I get? I get 3. How many do I get? Well, let's just be naive. This pair, or this pair, this pair. How many pairs? 3. So I get 3 times the same thing. And what do I get? I get v x minus x, right? So this is 1. And then the other one is also v minus x minus x. And x minus x is even 0. So it's v of 0. Squared. Boom. Don't worry, infinities have never been a problem here, right? So this integral will be the first divergent, this here will be the second divergent, but we will deal with it. And now, see this one, then we are done. Minus lambda squared over 2, 24, 24. 2025 would be fun. X, d, y. What do you want? Oh no, this is gonna be tough. How do you do this? I guess we have to write a little bit. You know, with all these computations, you never write it all out, but you scribble it. That's what we have. And with all contractions, there's so many. How many are there? Can you quickly figure out what 4, 5, 6, 7. What is 7 times 5 times 3? Well, that's not so bad. Why is it so many? Because it's just 105. It's 35 and 100. So we need 105 connections. So, and now we split them in different types. What can we get? We can get that, let's do, what do you want to do first? Let's do one from this group meets this group. Then we have to, I don't know. That's the one is the hardest. Let's say they stick to themselves. That's better. So if they stick to themselves, then this one has 3 parts. 1, 2, 3, and then we get what we had there, right? So that's one. We can have. So people draw this. This is the x vertex. This is the y vertex, and here come 4 arms out. And if they stick to each other, then they reach there, right? And they among themselves is this. But we have, and this is this picture here upstairs too. There's just one vertex x, and this is going from x to x, and from x to x the second time. Now here, that's happening there, and we have 3 of them. And they do their stuff 3 times, so we have 3 times 3. We have 3 times, we have 9 times this. We have 9 times the term, which is really just d0 to the 4th. Oh, good. 9 of them are accounted for. Now, let's say the other simple thing is, if all of them take hands from one and the other group, that's better. So, I guess all. So then, this needs to be somewhere here, and it has 4 options. Let's say this. This one needs to be there, has 3 options. This one has 2 options, and then that's what that. So this is 24. We get 24 times this. So we have 9 and 24. 33 somehow? 33 diagrams. 33 means we have 72 left. How do they look like anyway? And this is d x minus y to the 4. And now how do they look like? What is left? If you don't keep them separate and don't mix them, then it's, I guess then somebody needs to go across. Then we have 3 more arms on either side. We don't want to connect all of them across, so we have to have a bubble here and a bubble there, but then we have to also do this thing. So we need this thing. We need now. First, let's pick the ear. That means find a pair that stays among themselves. There are 6 pairs. 1, 2, 3, 4, 5, 6 pairs. So 6. 6 to select this ear, and then there's 6 to select the other ear. And once we have selected the ears, then we have to connect across, and then this X has 2 options left, and the other one doesn't. So this is how much? 36 times 2 is 72. Can you believe it? So now it actually works. This thing, the U between the bracket in the denominator is 1 minus I lambda 2 24 times 3 is 8 integral e4 x e0 squared. And then comes minus lambda squared over 2 times 24 times 24 d4x d4y, and then 9 times d0 to the 4 plus, what was that? 24 d x minus y to the 4. These are 100 propagators. And then we have 27, 72, 1 ear, another ear, and across the bridge. Boom. So if that wasn't exciting, we have even some Feynman diagrams. Thank you for your patience.
I have a question, since F probably the integral over d0 probably diverges.
It doesn't depend on x, so it's going to diverge, yeah.
Problematic when we forget higher orders. Wouldn't higher orders diverge even more?
Yeah, this is all problematic. So we're talking yeah, it's all. These are asymptotic expansions, they don't converge, they
It's a denominator anyway, so it's just supposed to be.
and so this is the denominator, exactly. So
So
if
you-
your denominator is infinity, we have 0, and then it'll happen, but except when we don't want 0. But the numerator will have the same divergencies and they cancel. In fact, the entire denominator will be a factor in the numerator. This is a lesson that you're supposed to learn at the end of this week. That the numerator can be factored into something, and the denominator is going to cancel entirely. These things are called vacuum diagrams because they don't know anything from the outside world. They just float. They don't have an x dependence. They are just by themselves. That's why there's kind of vacuum. And all these vacuum diagrams are going to go away. In the numerator, we'll have also vacuum diagrams, and they're magically canceled. And what then final rule will be, just write down the non-vacuum diagrams for the numerator and forget about the denominator. So there's something that looks all divergent, and we'll be able to throw away many of them and deal with many of them. And then there's still something that we don't know, and then the adjective we know. But I've said too much already. Okay, thank you again.